Hi, I'm Sneha Munisha, and this is my Physics 2212 Lab 6 on magnetic molasses. For the introduction, the purpose of this lab is to collect and analyze data of a bar magnet falling through an aluminum tube and comparing it with the computational models. We will use this data to estimate and show how Faraday's law works. Fundamentals used in this experiment is the Faraday's law, the Biot-Savart law, Newton's second law of motion, time derivative of magnetic flux on a dipole, and magnetic force. For the overview of the results, the experimental time taken is 1.21 seconds and the computational time taken is 0.815 seconds. The magnet was used to model a magnetic dipole while the aluminum foil modeled as a tube through which it fell. The assumptions in this experiment that we took are air resistance acting on the magnet is negligible, gravity and magnetic force are the only forces that are acting on the magnet, and the bar magnet acts as a dipole. For the procedure of this experiment, we first found the magnetic north pole of the magnet and then dropped the magnet down an aluminum tube 5 times, and then we calculated the average time it took to fall through the tube. We can see in this video that we are dropping the magnet and it takes a little bit of time before it falls down the bottom. For the system in this experiment, it is the aluminum tube and the magnet, while the surrounding is everything else in the room. The experimental data are the tube dimensions, where length is 0.3 meter, width is 0.006 meter, inner radius is 0.026 meter, and the outer radius is 0.032 meter. The properties of the magnet are the mass and the magnetic dipole of the magnet, which was 0.025 kg and 4.48 ampere meter square, respectively. The average time taken for the magnet to drop is 1.21 seconds. Here we can see that for each number of trials, we calculated the time taken for the magnet to fall, and then we calculated the average. For checkpoint questions, why can't we use a ferrous tube, for example, a steel pipe? Ferrous tube made from steel would have magnetic properties and would skew our data. What happens to the magnet? How does this compare to a magnet falling in free space? Magnet falls slower through the tube as there is upward magnetic force due to induced current. A magnet falling in free space would fall faster as there is only one force acting on the magnet, which is the weight. For the computational part of this experiment, we used a previous starter code where we updated the values that we got from the experiment and we computed the data using some formulas. For step 1, we can see that we updated the code by inputting our data from the experiment. These are some of the code that was previously given to simulate our experiment. Here we are inputting the mass and calculating the magnitude of the dipole moment, and we're creating a code for visualizing the bar magnet. For this part of the code, we calculated the magnetic field of the bar magnet using some formula, and then we calculated the magnetic flux and EMF in each ring due to the falling magnet. And in this part of the code, this simulates the loop, and finally, after calculating all the necessary data, we are printing the time taken for the magnet to fall through the tube. In this graph, we can see the velocity versus time plotting of the magnet falling through the tube, where there is a sharp drop in the velocity, and then after a few seconds, it reaches terminal velocity where the gravitational force is equal to the magnetic force. And at this point, the magnet exits the tube where the gravitational force is greater than the magnetic force. Interpreting the simulation, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicates current flowing in opposite directions. Which color corresponds to clockwise current and which corresponds to counterclockwise? According to Lenz's law, red is counterclockwise and blue is clockwise. What happens to the dynamics of the system where you flip the magnet around? Magnets falling would not change, however, current direction would be changed. How does the total time in tube of your real-world system compare to that of your computational system? Computational model is slightly shorter due to the air resistance and human error. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Gravitational force is greater than magnetic force when exiting the tube, but equal inside, as we previously saw on the plotting. Sources of error in this experiment includes human error and air resistance. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Lower resistance would increase induced current, creating stronger opposing magnetic field, and magnet would take even longer to fall. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Less current rings would be present in the tube, which would make an overall weaker opposing magnetic field, causing the magnet to fall faster. Thank you.